Hey guys, how's it going? So back again, it's been a couple weeks and I was actually taking a break here, and let me show you a few things that I've been working on. For anyone just joining, we're studying mechanical engineering theory for the math behind optimized start algorithms. Check out the paper in the PNNL paper directory on the repository. It's all based off of research, and we're trying to put it into code bases in Python and try and understand it. So we did get down to, we covered all three of these models: the model 0, model 1, the curved quadratic relationship. Model 2 was the linear, was model 1, which is then also has like a weather ratio factored into it, defined in the research paper. In model 3, this was the multiple regression, which we did in Python math libraries, which makes things a lot cleaner and easier. Then we briefly got into this model 4. Yeah, these are the equations here. Maybe I should have went over this, where we're at. But then this was the multiple regression equation, and then we started to get into this first order thermal response model, which is an iterative model, so it has some log mathematics, and that can be done in Python easily too. But what I wanted to do was actually step back to model 3. And in the past videos, I said we're just going to skip over the matrix algebra, but what I was really interested in is maybe doing like a little bit more deeper dive into the mathematics behind that, the matrix algebra, and also here too, model 4. So I created a couple bonus videos. So there's 2 more weeks of AI generated tutorial content, which I'm going to do, and I'll probably have to ask AI a bunch of questions, because my degree might have covered a little bit of this, but not super in depth with matrix algebra, linear algebra if you went for an engineering degree. And it's kind of a refresher, and I'm kind of learning some here too. So I've actually been implementing this in the Niagara framework on the Vibecoder repo. So I have a block that's doing it all. It's doing models 1, 2, 3, and 4, and model 0 actually. So I have these blocks running in the field. This is kind of exciting. So basically what it's doing is like the code running in behind the scenes here, it will start, it will predict all 5 models. So model 0, model 1, quadratic, model 2 is a weather bump, model 3 is the matrix algebra model, model 4, which is the first order physics model, has an enable feature to enable them. These are some learning features which we'll dive into. And then it's working. It's I've been kind of with the help of AI, like putting all of these into it's getting to be like 1,500 lines of Java to do this, and then all of the model 3, the requiring linear algebra for multiple regression, that's here, in model 4. So it's, from I can see, it's working. There's a lot going on behind the scenes. So like traditionally in optimal start, they've only been doing a simple degree per minute model. Linear model is what the paper calls it. So this is, we've talked about this in the very first YouTube videos. It's just, this is model 0 essentially. And then we get into these more elaborate math models here. And I decided originally I was not going to do this model 3 and 4 because it was just getting kind of complicated. Now it's really complicated, but it appears to be working. So have yet to really put this through its paces in the field, but some early tests. I've also been adding in a lot more error parameters that the block is calculating. So when we're predicting minutes, here, like this is not showing like what it's actually predicting right in the moment, because this would have been early in the morning when I'm still sleeping. But when the model last ran, it predicted 19.3 minutes. So this is what the other models predicted right here. And then like what I wanted to do was there's actually, I'll show you in a second, history days to retain. So this is actually runs. So this would be every time the block runs, which we've been talking about in the previous videos. We snapshot the delta temperature, which is the zone temp and the target zone set point. And I have a tolerance built into that, and we're outside air temp. And then there's a unit of time in minutes. So then that's how we're running all these different math models across that. So like what I'm trying to do is also track squared error and averaged squared error. So over time, there's another parameter in here called the auto mode. So after 3 days, we'll start actually controlling to the model that has the best squared error over time, average squared error over time. And as you can see in here, like we're predicting where the model 2 is actually has the best average squared error. If we get into some of these, a few other parameters, if you look in the AX property sheet view, this is on a VRF system, VRF cassette Daikin system in the field. This is basically our last runs from our different math models, predicting minutes, and this was our actual warm-up time. So like the computer science pattern that we've been talking about actually snapshotted 15 minutes is the actual delta temperature, and then these are what our models are predicting. So the linear model was pretty close. That was the closest one. But I think as you get more data, that 40 days of data to retain, these models, according to the research, will start predicting better. And the average squared error will get better over time, and then the block will just start controlling using that best model. And the paper says that they found that model 3, the multiple regression model, performed the best. And I'm really curious to see if I get the same results. So yeah, it's pretty exciting. So there's also some, I have a point here that maybe I can start trending this too, that we can start logging some of these metrics, that the best model, at the moment it's model 0, but maybe this could be, whatever, model 3 according to the paper. So yeah, this should be really interesting to see. I'm really wondering too if it's dependent on the type of building, like the paper suggested, if the outside air temperature is factored in, if the zone temperature, the delta temperature is affected by outside air, which exterior zones to buildings definitely are. And also the time of year. So I'm kind of wondering if that will, like one model maybe will perform better in the summer or shoulder seasons or dead of winter. I don't know. So I'm dying to see what that looks like. Okay, so enough on that. So I think like this is what I'm hoping to go back to is model 3. So we briefly introduced this on the last video, days 29 and 30. And then I want to go to this bonus content created by AI, so to help study the matrix algebra behind here, and then also some of the theory behind first order iterative models here. So we're getting there. This is like a 50-day challenge, which is now turned into 64-day challenge with 2 extra weeks of content. So I'm learning a lot. So I don't think if I pushed myself to do this challenge, I would have never pushed myself to keep on, making these blocks a little bit better or more bells and whistles. So it's helping me learn as well. So any of the PhDs out there, guys and girls with really you're fresh out of engineering school, if there's something that you see that could be improved that I'm explaining wrong, let me know. I'm still learning too. So I'm really excited to test this on the live building automation system as well. So, okay, so enough about that. Okay, so here we are. I'm in the lessons directory. We stopped at here. Now I'm going back up to bonus day 1. So let's just do this. I think we can get this out of the way, and then tomorrow we'll go back to bonus day 2, and then eventually get through all the bonus content, and then maybe we can chat about just pick it off on day 31, I think. Okay, so here we are. So vectors and dot products. So this is running model 3. So we were using scikit-learn linear algebra and then also the NumPy computing library. So what goes on behind the scenes that we don't see or have to worry about is all this linear algebra, matrix algebra. So our code base looks very nice and clean when we can use a math library, but these blocks that these guys, we don't have that. So I used AI to help me do some of the matrix algebra by hand, and I'll show that to you later. And I'm still working on this VRF system, all degrees Fahrenheit here. So like as it gets cold out in the winter, it's the winter where I'm at right now, these exterior zones, they cool down when the HVAC system isn't running. So that's what we're trying to do here. So okay, so let's just go to our math lesson script. Anyone out there that needs help getting set up in Python or how to clone the repo, and just let me know. More than reach out to me on LinkedIn. That's the easiest way. Okay, so here we go. So a vector is just an ordered list of numbers in optimal start math. Vectors represent temperature errors over time, model coefficients, rows and columns inside matrices. So this is the data that we capture basically. A dot product combines 2 vectors into a single number. Dot AB equals alpha B plus alpha B2, whatever they're trying to show. So anytime you have a weighted sum, like time equals D plus alpha times temperature delta plus B times delta temperature times weather rate, the weather factor. I think this is model 2. Matrix multiplication is nothing more than repeated dot products. Mini example. So here we go. So let's just try this. Hopefully this first one is pretty easy, but I do think it gets really hard really fast. So I'm definitely going to have to be asking AI for some help. So math lesson script. Okay, so 32. So what is it doing here? So it is, okay, so we just have like a little list or like an array like data structure, and this dot value is 0, then we're gonna for loop through the range of this list. So that's 3 times. So then it looks like we're adding these two values times each other, plus these two values times each other, plus these two values times each other. Looks like 32. Seems pretty straightforward. Compute the dot of these two. Okay. I don't know why I copied this, but I like to copy and paste things. It just makes things a little easier. Kind of funny that it recognizes the AND operator in Python. So what's our dot product here? Ooh, 24. So that makes sense because 2 times 10 is 20, 4 times 1 is 4, equals 24. Why must vectors be the same length? That's, you can't multiply values. That if this was 1 longer, that would error out. Where does the dot product appear in Model 3? Ooh. Okay, so write your own dot product script using a for loop only. Okay, so I am going to trying to think how this. I actually don't know that off the top of my head. Model 3. So I know the dot product would be used when this is fit, when the multiple regression is fit. You know what, I'm just going to do I am just going to a fresh session of ChatGPT. Where are we here? So give it that for some context. Bonus day. On the lesson I am doing, let me give it some more context. Let's see, where are we? So, sorry. So, I'm jumping around here a whole bunch. Sorry about that. Lessons. Bonus day. Let's see, so I'm going to just paste this because I had some in there. So, I'm on. So, I'm on the lesson I'm doing. Okay, on the lesson I'm doing bonus day 1, the question, where does the dot product zoom out? Is that in the multiple regression when the model is fit? Please elaborate. I'm just gonna erase this. Alright, so ChatGPT is reading. Yes, your instinct is correct. Explicitly at prediction time is a weighted sum of features. So Model 3 is rewritten in dot product form. Aha. Okay, cool. So this is interesting. X equals delta temperature, dot product, delta temperature times the weather factor times and coefficient. Interesting. there are two different dot products involved in regression. This is where people get confused. Prediction time dot product, runtime, training time dot product when fitting the model. Model 3 is fit using multiple regression. The math internally uses many dot products. So this is why the multiple regression gets kind of complicated. You usually never see this, especially because libraries hide them, like NumPy and scikit-learn. Ordinary least squares regression is just dot products stacked inside matrices. Why this matters? Cool, I think we answered that. Write your own dot product script using a loop only. Okay, so think if I would do this, I could just rewrite. I'm just gonna cheat here. I'm just gonna recycle their code. Just say dot equals dot plus. So I just kind of, this is also using a for loop, so it's just a different way of adding the dot product together. So I kind of did a little bit of cheating there, but I think I'm just gonna end it here, guys. So hopefully this makes sense. It's just like a little bit of computer science slicing right here. So we're just, the I is this for I in range, that would be a value of 2, and then I becomes, you know, either this value or this value. And then I'm just dot equals dot plus these two values times each other. So okay, I think that's a good place to stop. I definitely have a lot to learn here, so I'm looking forward to seeing you guys on the next one. Have a great day.